All right, so on to measures of spread. So measures of spread, some of this is going to use our measures of center. So one of the things I mentioned a while back was that when we were talking about when should we use a mean or when should we use a median. And I said if we had data that had that bell shape, we like to use a mean because there was a lot of extra things that we can calculate from a mean. And this is where we're going to start some of that because things that we can do is we can calculate variance and standard deviations if we have means. And those standard deviations and variances really mean anything useful as long as we have bell-shaped data. Okay, oops, let me get that a little smaller. Just to kind of show you what we're measuring here. So suppose you decide that you're deciding between living in San Francisco and St. Louis. I already know I don't want to live in St. Louis, but anyways, one thing you might consider is weather. So this table here is representing the average monthly temperatures in degrees Fahrenheit in both cities. So you're going along, and what we see is that San Francisco, so you see it right down here, as temperatures are staying pretty much in the 50s and the 60s. There isn't a lot of variation. Whereas St. Louis is in the Midwest, so it has a lot more fluctuation because San Francisco lies along the ocean and it lies along a stream of water that keeps that area kind of temperate. St. Louis doesn't have that luxury. St. Louis, like I said, smack dab in the middle of the country in the Midwest. And what we see here is the temperatures really fluctuate. So we get lows in the 30s and we go up to almost 80 degrees in the summer. So what we have here is a situation where San Francisco is temperatures stay pretty temperate. They don't move around a lot. They're pretty close to each other. You're pretty much expecting every day to be somewhere between 50 and 65. Where St. Louis, part of that year, you're going to be cold. Part of that year, you're going to be pretty warm. It's going to vary quite a bit. So mean in these cases, so if we talk about both cities, so San Francisco, its mean temperature is 57.5, and then St. Louis's mean temperature is 56.1. We don't have a lot of I mean, the means look about the same. So you look at both those means, it's like, well, they average around, upper 50s. Except when you look at the rest of the data, you realize, well, yeah, but San Francisco stays a kind of consistent temperature and St. Louis is all over the place. So what spread measures and things like variance and standard deviation is it measures the spread from the center. So like this is my center, and we see we don't spread a lot from that center. We're here, St. Louis, we got a lot of spread from that center. That is what your standard deviations and variance measure is that spread from the center. And we do care about that because it's going to give me a lot of information later on about my data. And what we see is that when we have the smaller amount of spread, we're more consistent, and when we have this larger amount of spread, we're less consistent. And sometimes we really want that consistency, and sometimes we don't. So for my first measure of center, we're going to pick one that, or not measure of center, I'm sorry, measure of spread, we're going to talk about range. The range is probably one of the least useful of them. There you go. My slides got stuck there a little bit. Range is really our simplest way of measuring spread. So it just really tells me like how like how many numbers is my data spread out. So the range of the data set is the difference between your largest value and your smallest value. If we look at San Francisco, for example, San Francisco's lowest temperature is 51 and its largest is 53. So its spread is 12. It means that temperatures spread out between 12 degrees. That's how much spread we have. As a comparison to Texas, which is in one day, the spread in your temperatures could be like 30 degrees. But you got San Francisco where it's staying pretty consistent all the time. Then the range for St. Louis, so 30 is the lowest temperature we have in St. Louis, and 79 is the largest we have in St. Louis. So the difference between those is 49, so almost 50 degrees. So although range is easy to compute, it's not often used in practice because it only involves two values in the data set. There's not a lot I can do with that. I can look at it and go, okay, San Francisco is a little more clustered in its temperatures, and St. Louis is much more dispersed, spread out in its temperatures. But that doesn't tell me a lot of information. It just, like I said, it just tells me which one's a little more spread out and which one's a little more consistent. But what we need is we need other kinds of measures of center, or measures of spread. I just came off doing measures of centers video. So we're going to compute variance of a population and a sample. So variance is also not particularly helpful for us right now. It's some of those things that becomes a little more helpful if you do more statistics in the future. So when a data set has a small amount of spread, like the San Francisco temperatures, most of the values will be close to the mean. When the data set has a larger amount of spread, more of the data values will be far from the mean. Makes sense, right? The variance is the measure of how far the values in the data are from the mean on average. So the difference between this and range is measuring from your smallest to your largest, and it's measuring that range there. This is measuring from the center of your data out to the edges. So this is a measure from the center of data. So it's a little different. So it's telling me how I range from the what's really like what's average, what's expected. So variance is computed slightly different depending if we're talking about populations and samples. And the calculation variance is as part of the calculation for standard deviation. So we'll also see that standard deviations will vary slightly in its calculations depending if we're talking about a population or a sample. So in most cases, calculations between populations and samples are pretty much consistent. It's just with like variance and standard deviation that we're gonna see things are a little different. So population variance. So we're going to let x1, x2, x3, yada, 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 denote values in a population of size n. So they're my data points. So remember, because we're talking about population, we're talking about population size, capital N. And then mu, if you remember, is population mean. So this is all about population. So what we use is we use this symbol here. That symbol is called sigma. And really, it's what it is. It's a Greek F. So we had a sigma before. We had this sigma. This is like the capital version, and this is like your lowercase version. We don't really care about this sigma right now. We're caring about this lowercase sigma. But what we do is we have a summation of x minus the mean, and we square that. So we call that actually a square deviation. And then we're going to divide by a capital N. So we're going to run through a little bit of how to calculate this by hand, just so you understand the process. But later we're going to look at the TI-84, and it'll be a lot easier to do calculations with an 84. Get that centered. So we're going to compute the population variance for the San Francisco temperatures. So San Francisco, like I said, that one had a small range in its values. Everything was very clustered together. So what we're going to do is we're going to first compute the mean of all this data. So if we add up all those temperatures, we're going to get 690, and then we have 12 months that we're looking at, so divide by 12. And what we're getting, and like we said, we already found that had this mean earlier, but the mean temperatures for San Francisco is going to be 57.5. So for each population value x, we're going to compute an x minus the mean. So what this is here, or sorry, down here, this, I just take 51 and I subtract 57.5. That gives me a negative 6.5. This right here, I take that 54 and I subtract the mean again. So I'm going to subtract that 57.5. That's going to give me a negative 3.5. We do that for all of our data points. And what we have here, this is essentially what we call a deviation. And it's the deviation from the mean. So what we're saying here, 51 is negative 6.5 degrees cooler than the mean. That's how far it deviates from that mean. 68 is 2.5 degrees hotter than the mean. So it's telling you it's all a comparison to the means. How far am I from the mean? So essentially, it's supposed to be a distance from the mean. All right, and since, like I said, a deviation is technically a distance. So this is a weird part. So we like distances to be positive. So the way to make it positive was we square it. So this is your, like I said, deviation from the mean. This here is what we called a squared deviation. So the reason I'm making that squared deviation is we don't want a negative value because actually, if you do this correctly, all these deviations, they should actually sum up to 0. So it's not very helpful if it sums to 0 because I'm trying to figure out an average distance is essentially what I'm looking for. So what we do is we square everything to make it positive. So like this value here, 42.25, well, that is just negative 6.5 squared. This number right here, well, the deviation is 2.5. So if you take 2.5 and you square it, you're going to get 6.25. We just take those deviations and we square them to get these numbers. And the reason I do that is you notice that once I square, that's all positive. The next step is that we want to do a sum of these squared deviations. So we're going to take this whole column and we want to sum it. So the sum of your squared deviations is just going to be this whole line of your deviations added up. So the 42.25, the 12.25, yada, 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 all those numbers, and I get 169. This is just the summation of your squared deviations. And because essentially what we're doing is kind of like an average, so we got that distance there. What we're going to do is we're going to take it, that sum of your squared deviations, 169, and we're going to divide by that sample size or population size of 12. So this is the sum of the deviations, squared deviations of each month from the average. This is how many months we had. So this is your essentially mean squared deviation from the mean. Which we kind of going, I don't know what that means. I totally understand that. It doesn't really make a lot of sense. Remember that deviation is a distance. So it's the average squared distance from the mean. So this is very close to like doing a mean of distances. It's just a little different because of that squaring in it. So when we calculate, when we find what we call our averages, because really the good word for this would be an average. So an average is pretty much any kind of measure of center that we have. Averages, there are several calculations for different averages. We're kind of doing it as like, this is our own calculation, awfully based off a mean calculation that is just figuring out an average squared distance from the mean. So for us, this is not going to have a lot of meaning. There are some good things about variance. Like I said, the meaning's not very clear in a real world sense, but it is a estimate that is non-biased, which means that it's not going to tend to be too low or tend to be too high. If we do sample variance, there's a slight change here. So remember this dividing by n? Well, we're going to divide by something a little different. So when the data value comes from a sample rather than a population, then we're going to have sample variance. The process for computing sample variance is a bit different from the one used to compute population variance. In this formula, the mean is going to be replaced by x bar because we want a sample mean. So we have our x's minus x bar, so we subtract sample means instead. Then we square those and do a summation. We don't divide by, remember, n is sample size. So we don't divide by big N altogether. We divide by the little n, so how many numbers we have in the sample minus 1. And we do that minus 1 because it's going to fix errors in the calculation. So we had always said that when you do samples, samples do not always reflect the population perfectly. So a way to, we found that with sample variance, a way to make sample variance look closer to what population variance should be is we do the subtract 1. And then, as you're going to usually see is the case, when we talked about mean, population mean used a Greek letter mu, sample mean used an X bar, so we used an English letter. When we were talking about population variance, we used a Greek letter sigma squared. And then here, we're actually going to use x squared, so we used an English letter. So we pretty much, for samples, we use English letters. For populations, we're going to use Greek letters. So we get x squared, which is my sample variance, is going to be the summation of x minus my x bar, so my sample means, and then we square each one. Then we're going to divide by sample size minus 1. We divide by the n minus 1. So when computing the sample variance, we use the sample mean to compute the deviations. So for population variance, we use population mean. So because there is a little small difference between a sample mean and a population mean, and we're doing all that squaring, so the little difference that we have there between a sample mean and a population mean is exponentially bigger when we start doing a not standard deviation, when we start calculating those deviations. So what it is a small difference in that sample mean from that population mean tends to explode in the calculation for variance. So what we found is that if we divide by n when computing sample variance, the value would tend to be a bit smaller than the population variance. So it is it underestimates. It's biased in one direction. So to kind of correct that bias, we do that n minus 1 because it forces that that sample variance, also the standard deviation, but forces that sample variance to be a little larger and a little closer to your population variance. So it's just a correction because of really what it's going to be is sampling errors. So sampling errors are going to cause a little difference. The sampling errors we can't do anything about. It's going to cause a little difference in those calculations. So that minus 1 kind of corrects it. So sometimes when you're trying to compare these, it doesn't look like a correction. So we're going to do this one by hand. I give you a few values. So a new type of battery is being tested for a laptop computer. The lifetime in hours of 6 batteries are 3 hours, 4, 6, 5, 4, and 2 hours. We want a sample variance for the lifetimes. So I would suggest building yourself a little chart. If you want, you can pause this, but let me get to the chart at least. I might have too much chart here. We'll fix it. So this is going to be your X's. So that's those battery life times. One of the things you're going to want to calculate is you want to figure out what the mean is. And once you figure out that mean, you're going to take each X and you're going to subtract the mean from it. Then after you do that calculation, you're going to square them. And that was, like I said, I made this a little too big. But that is a part of the chart that you're going to really need. And then remember that what you're going to need is a summation of those x's minus x bars squared. Because when in the end, what we're going to have is when we talk about that variance, it's going to be this x minus x bar squared divided by n minus 1. Okay, so like I said, you're going to figure out that mean first so you can have it to do these calculations. I'll give you a bit to do that, practice it, and then we'll go through it. Okay, so if I figured out that mean, the summation of those variance times is 24. There's 6 of them. So what we get as a mean is going to be 4. So what we're going to do here is that we're going to find that deviation first. So 3 deviates from 4 by minus 1. And then what I want to do is I want to do my squared deviation. So we turn it into a positive. So -1 squared should be +1. Then we're going to have 4 minus 1, so that is 0. 0 squared is 0. We're going to have 6 minus 4, which is 2. 2 squared is going to be 4. We're going to have 5 minus 4, which is 1. 1 squared is 1. We're going to have 4 minus 4 again, which is 0. 0 squared is 0. And then we're going to get 2 minus 4, which is -2. And -2 squared should be 4 again. So if I add these up, we have squared deviations of 1, 0, 4, 1, 0, 4. So that is going to be 10. I'm double checking something here. I feel like the number is not coming out right. That can't be right, is it? No, I'm right. My calculator was calculating standard deviations. So no, we got that. So we got, and then my sample size, we had 6, but we subtract 1. So this is going to be 10 divided by 5. So my sample variance is going to be